Hello, my name is Mary Freeman Holstein. I'm a math teacher and tutor, and this is an introduction to calculus. I remember growing up that of all the subjects taught in school, we kind of knew what biology would be about. We knew what geometry was, but calculus, that was the only subject that, unless you were actually taking it, nobody really knew what it was. So we're going to fix that today. If you have even just the tools from first year basic algebra, you can already begin to do some beginner calculus, and it's way too much fun to let the rocket scientists keep this one all to themselves. So let's dive in. You can look on the description to the video and download the PDF file, which will help you take some notes as you follow along. Okay, calculus boils down to two big concepts: derivatives and integrals. So our goal for this lesson is that you are going to know what those are and begin to see how someone would go about finding them. So what is calculus though? We are going to be studying variables that change. Variable is measuring anything you would want to measure that changes over time. Some examples: the ice cream cone sales in your business, the average daily temperature in your town, what's happening with the population of spotted lanternflies in your state. So many things in life don't stay the same, they change, and you want to measure them and have some math tools to analyze them and know more. And one of those tools is finding the derivative. A derivative is a rate of change. So we're going to look at the my favorite example of a rate of change. It has to do with traveling. Let's say you're taking a car trip and you're looking at the speedometer to see how fast you're going. That is a rate of change of where your car is, how far away you are from your starting point. This is my little alien friend, Zorg, and he has an alien high-tech car. It can instantly go from being at rest to whatever speed he wants it to go at, and that's going to simplify the numbers for us just a little bit. Zorg gave us a graph as a quick way of giving us lots of information about his time and his distance. So we're going to look at this graph, turn it into a story so we really understand what's happening with this trip, what kind of driver Zorg is, and if we take that information and convert it into something about his time and his velocity. Velocity, remember, is your speed, but with direction, so either going or coming. We will be taking the derivative of this top graph. If we go from distance to velocity, we're looking at the rate of change of our distance. That is the derivative. All right, so what can we find out from this graph? Zorg starts off in his car at our first data point, 0, 0. So time, 0 hours past noon, that is noon, and distance from home, he's 0 miles away. So he is beginning in his driveway for a start. I'm gonna put that at the beginning of his journey. He is also at time noon. He is going at 0 miles per hour. That makes sense that he starts off holding still. So what can we find out about his car trip? It looks like our next data point is at 1 o'clock. He has gone 20 miles away from home. So we can think really fast in our head. 20 miles away in just 1 hour, and he's using this nice car that instantly speeds up and holds a constant speed. So he has maintained 20 miles an hour for that whole first hour of time. All right. Then what happened? Well, between 1 and 2 o'clock, Zorg is now 40 miles away from home. He's traveled another 20 miles, and he's keeping that same constant speed. So the story piece, we could say 20 miles an hour, Zorg, we already know he's a very careful driver, and he's probably on local roads, not going very far. 2 hours of that. Next in his story, between 2 and 3 o'clock, his distance stayed the same. So he is down at velocity 0 miles per hour. He must have taken a break. Maybe this is a snack break or something. And we keep going with our story. So between 3 and 4 o'clock, he is now gone up to 50 miles from home. He's moved 10 miles. Wait a minute, 10 miles in an hour? Oh my gosh. So you're going at 10 miles an hour. I think he's in a traffic jam. This is not fun. What happens next? Between 4 and 5 o'clock, he only gets another 10 miles. He's 60 miles away from home and stuck going 10 miles an hour for 2 solid hours. Okay, Zorg must be getting super frustrated and bored, I imagine, in this trip. And what happens? Well, between 5 and 7 o'clock, his distance stopped changing. It's staying at 60 miles away. So yeah, I totally understand why Zorg would want a full 2-hour dinner break. Absolutely. He's going to figure out, what do I do? And then what happens the last hour of this graph? Well, his distance goes from 60, boom, down to 0 miles away. Wow, he covered 60 miles in just an hour after all of that. He must have sped up. He's going 60 miles an hour. So I think after his dinner break, he got on the interstate. The traffic jam is gone. And we need to show on our velocity graph that he's turned around. He went back home. So his distance is going the other direction. We can show that with a negative velocity, 60 miles an hour, but in the other direction. All right, so we just used some basic addition and subtraction to get his velocity graph. We did take a derivative, but calculus and math in general is all about patterns and shortcuts. I would really like a shortcut to get my derivative for other more complicated graphs. And if we think about what we know about velocity, we do have an equation. Velocity is distance divided by time. Do units check, miles per hour. Yes, that is the right units for velocity. And if we think about what that means on this graph, well, the graph we were given to start off with, distance was the height and time was along our x-axis here, our width. We are looking at change in y values over change in x values. Let's throw in some fancy math notation. Delta y over delta x. Do you remember the slope formula from algebra? Change in y over change in x. By the way, delta, this triangle, is the Greek letter that means we're taking the difference in something, the change in something. So change in y over change in x, it's the slope formula. Oh my gosh. So when we did this a minute ago, getting the velocity, we were actually just pulling the slopes off of the graph. That's a very powerful shortcut. And even if this had been a curve instead of a nice straight line, we could use some tools for math to figure out the slope. How steep is it going up or down? But I'm getting ahead of myself. Let's double check that this is definitely true. The slope of this line between 0 and 2, rise over run. Rise 40, run 2. 40 over 2. Is that a slope of 20? We did plot 20 for our velocity here. 0 slope, where the line flattens out. That was 0 velocity. That checks out. Let's do the last piece. 7 and 8 o'clock, we were decreasing slope, going back towards the house. We went down 60 over 1, negative 60 over 1. Yes, we matched that at a negative 60 velocity. So derivative, the rate of change, when we're going from distance to velocity, we're just taking the slope. That's a fantastic shortcut. And now you're ready to go in the other direction. Let's figure out what's an integral. Integral. So an integral is when you start off with the rate of change and you want to go backwards, integrate all that information together to get the original variable and find out what it was doing. So we already went derivative this direction. If we go back up, that's an integral. And we could, let's jump straight to the shortcut this time. We already worked out these numbers. How could we go backwards? So picture yourself, you're a passenger in Zorg's car and you're looking over his shoulder and you're jotting down the numbers on his speedometer. Could you then, run some numbers in your calculator really quick and figure out how far you had traveled? Yes, you can. We are going to look at, for our shortcut, we want to get information about distance this time. So let's write an equation about distance. Distance is velocity times time. Do a units check. Miles per hour times hours, you get miles. That's what we want. That's the equation. And if we think about what this means on our graph here, we have velocity is our height, our y values. I'm going to put h for height. And time is our x values. That is widths. Height times width, or we might think of it as length times width. Does that sound familiar? Oh my gosh, it's the area of a rectangle. Just the area formula. That's it. So, if we want to shortcut taking an integral, we could look at the area values on a velocity graph, and that will give us information about the distance graph. Let's check this out. The area of this first little rectangle, first part of a rectangle, going from from noon to 1 o'clock, it has a height of 20 and a width of 1. 20 times 1, we have 20 miles. That is in fact what it's supposed to be. Let's see, if we had done the whole rectangle to get 2 o'clock, we would have said, well, height of 20, width of 2, 20 times 2, 40. Yes, it would be 40. As we go across and we get to the next thing, well, at 3 o'clock, we found this area, but we're adding 0. The area under a line is 0, nothing there. So it should stay at 40. It did. What's the area of our next little rectangle? Well, it has a height of 10 and a width of 2 hours. So plus 10 times 2, or we can think of that as plus 20. 40 plus 20, we have 60 miles we've gone. Yes, this is all matching up. And then my favorite piece, I know that your whole life up till now, everybody has been saying the area of a rectangle is always a positive number. You can't have negative area. In calculus, yes, you can have negative area. We need the area of this last rectangle to count as a negative number, because when we add it to the 60 miles that we've gone, we really need to get back to 0. He's going home. I don't want to show his odometer where it's like the total miles he's traveled. I want to know how far he is from his house. So negative velocity, negative area, all of this, we really need that to get his distance from his house. We're going to add negative 60 area. This is a width of 1, height of negative 60. That gives us 0, and boom, our distance graph is at 0. So the shortcut, when you are taking integrals, we are actually talking about the area under your derivative curve, or in our case, we were going from left to right and we were looking at these little nice rectangle areas. When you add up all those areas, it takes you back to your original variable, the distance. That's it, that's calculus. We did derivatives, we did integrals, and I say thank you, and Zork says thank you.